गुड मॉर्निंग। आज हम माइक्रो इलेक्ट्रॉनिक्स में टीएम मोड इन सर्कुलर वेवगाइड डिस्कस करेंगे। लास्ट टाइम पे हमने टीई मोड किया था, ट्रांसवर्स इलेक्ट्रिक मोड। आज हम कर रहे हैं ट्रांसवर्स मैग्नेटिक मोड। इसी नाम से क्लियर है कि ट्रांसवर्स मैग्नेटिक मोड मीन्स द हॉरिजॉन्टल कंपोनेंट और दैट इज द component of the magnetic field along the direction of the propagation of the wave, Hz will be 0. But in this case, Ez will be not 0. And for this case, the Helmholtz equations for the Ez can be written del square Ez equal to gamma square Ez. Solution of the equation is per we have calculated for the TE mode. We can write Ez equal to E0z Jn the function of KCR cos n phi e raised to power minus j beta z. Means there are the three components which are related with the r, phi and z. The boundary conditions for this at r equal to a means at the circumference of this one the tangential component of the electric field Ez will be 0 at r equal to a. So by using this one you can write Jn KCA equal to 0, and we know that the J is the function of the KCA 0 have the very large number of the solutions, infinite number of solutions, or we can say infinite number of the roots. So the possible values for the x and f, that is the can write np, that is KCA, are given as below. N equal to 0, 1, 2, 3 we can write. Then these are the values, numerical values, no need to remember this one. And we know that the Maxwell equations for these two fields, electric and magnetic field, that is del cross E equal to minus j omega mu h and del cross h equal to j omega epsilon E. Using the cylindrical coordinate system, we can obtain the components of electric and magnetic field like we have calculated in the TE mode, that is equal to 1 by r del Ez by del phi minus del E phi by del z equal to minus j omega mu hr. Similar for the h phi, del Er by del z minus del Ez by del r equal to minus j omega mu h phi. And the last for the hz component, 1 by r del by del r of the r e phi minus 1 by r del er by the del phi equal to minus j omega mu hz. And using the next equation for the electric field, we can calculate 1 by r del hz by del phi minus del h phi by del z equal to j omega epsilon r er del hr by del z minus del hz by del r equal to j omega epsilon e phi. And the last 1 by r del by del r of the r h phi minus 1 by r del hr by del phi equal to minus of plus of the j omega epsilon ez. But the z component of the field is given by the e raised to power minus j beta z. So del by del z can be written like this one, minus j beta and hz equal to 0 for the TM mode. So substituting these two values, we can obtain and rearranging the equations like the electric mode, Er equal to minus j beta by the kc square of multiplied by the del Ez by del r, E phi equal to minus j beta kc square multiplied by the 1 by r del Ez by del phi, and Ez we have given like this one by the method of separation of variables. E0z equal to jn function of the KCR cos of the function of n phi e raised to power minus j beta z. And the magnetic components, hr equal to j omega epsilon kc square multiplied by the 1 by r del Ez by del phi, and then the h phi equal to j omega epsilon kc square del Ez by del r, and last as we know for the TM mode hz equal to 0. And here we have write kc square equal to omega square mu epsilon minus beta square. So for the TM mode, different characteristics we can calculate using these electric and magnetic components, and here we start from the propagation constant beta. We know very well the beta is given equal to root of the omega square mu epsilon minus kc square, and here kc equal to x n np by the a. So this is the beta. Now the cutoff wave number for beta equal to 0. Use beta equal to 0 in above equations, that is omega c square mu epsilon equal to xnp square by the a square. So xnp equal to kc minus equal to omega c root of the mu epsilon, and cutoff frequency fc, that is 1 by 2 pi a xnp by the root of the mu epsilon, and the phase velocity vp, that is given by the omega beta, and that is 2 pi f divided by root of the omega square mu epsilon minus omega c square mu epsilon. And by using calculation we can write the c divided by root of the 1 minus fc by the f whole square. And similarly for the guide wavelength, lambda g or the lambda, that equal to lambda 0 divided by root of the 1 minus fc by f square. And then last wave component, wave impedance for this one, tm mod tm equal to beta by omega epsilon, and that is equal to the eta multiplied by the root of 1 minus fc by f square, where eta equal to root of the mu by epsilon. Now what is the dominant mode in the circular waveguide? As per we know, that is the dominant mode, the definitions, the mode which have the lowest cutoff frequency or the highest wavelength. So in circular waveguide, using the table, it is observed that for the TE11 mode they have the lowest cutoff frequency, and hence it is the dominant mode in the circular waveguide. And for this one KCA equal to 1.841, the same table से calculate करते हैं. So the lambda c for the TE11 mode is 2 pi a by x dash 11, and that is 2 pi a 1.841 a, as per we have calculated in the TE mode. This is cutoff wavelength. And using this one dominant mode, we can also calculate the degenerate modes in circular waveguide. As discussed earlier, the TE11 mode have the lowest cutoff frequency, and hence it is dominant mode. Now it is also proved that for the TM mode, P0m equal to P1m. Hence these two have TM01 and TM1m modes have the degenerate modes, means both have the same fields and the same cutoff frequencies, some frequencies, so they are called the degenerate modes in the uniform circular guide. Now what are the field patterns of the electric and magnetic field in circular waveguides? General rule for the field patterns in circular waveguide is given as this one, that for the TENP and TMNP, where n represents 0, 1, 2, 3, 4, 5 like, and this, so the number of full cycles of the field variations in the one revolution through the 2 pi radians or the pi or the 360 degree you can say, means complete rotation के लिए कितना इसका change होता है वो देख लेते हैं. And P equal to 1, 2, 3 indicates that the number of zeros of the E5, that is J and S, KCA लिखा था अपने उसके according along the radial of the waveguides. So for the TENP mode, TE11 mode, dominant mode, have the electric field lines are the curved and the meets at the perpendicular right angle in the inner surface of the waveguide. So फिगर से क्लियर है कि ये जो डार्क लाइन्स है, ब्लैक लाइन्स है, वो इलेक्ट्रिक फील्ड लाइन्स है, और इनकी खासियत ये है कि दे आर इन द कर्व फॉर्म. नंबर सेकेंड, they meet the circumference at 90 degree. And similarly dot lines जो red से indicate की है, that is magnetic field lines, and that is in perpendicular to this one, both are perpendicular to each other for the TE11 mode. Now field pattern for the TMNP mode. Electric field lines are the radial and the magnetic fields loops are concentric. तो इसमें जो फिगर बनता है वो इस तरह से हो जाएगा कि जो इलेक्ट्रिक फील्ड लाइन्स है वो डार्क होगी, टुवर्ड्स द रेडियल हो जाएगी, एंड द मैग्नेटिक फील्ड होगा वो इस तरह से लूप बनाएंगे गोल गोल, और एक कॉन्सेंट्रिक रेडियस की तरह से दिखाई देगी कि जिसकी रेडियस थोड़ी थोड़ी बढ़ती जाएगी. दे आर द मैग्नेटिक फील्ड्स. सो दिस इज ऑल अबाउट TM mode and the electric field pattern mode. These two modes having the dominant mode and the degenerate mode. Okay, thanks.